అయిపోయింది కదా. సేమ్ లింక్ రాదు.
Hi everyone, good afternoon.
Good afternoon, sir.
Okay, madam. Please let me know, madam, when can I start? I see just 12 people here.
Yes, sir. So 5 minutes
Sorry.
we'll wait for faculty to get participant to join, sir.
Okay, madam. No
Yes, sir.
problem.
Yes, sir. Hare Krishna, sir. Sir? సార్ ఆ అమ్మాయి దీప్తి జాయిన్ అయింది సార్. మీరు జాయిన్ అవ్వలేదా? అమ్మాయి వచ్చి వెళ్ళిపోయినట్టుంది. లెఫ్ట్ ద మీటింగ్ అని వచ్చింది. ఓకే సార్.
Good afternoon to one and all.
Deepthi, you can start, ma'am.
I take
Yep.
yes, ma'am. Yeah, good afternoon to one and all. I take the pleasure of welcoming you all for the session 2 of our phase 1. Session is about to start. Kindly wait for a few minutes. Thank you.
सब जैन गंडे जैन गंडे
Sir, mute చేసుకోండి.
I request everyone to please mute your mic and turn off your video.
Sir, shall we start, sir? Sir, Dastagir sir.
I'll,
Hello.
Madam, can you hear me now?
Yeah, yes, sir. I can hear, sir. Shall we start now?
Okay, madam.
Yes, sir.
Yeah, no problem. I'll start.
Yeah, Deepthi, you want to tell anything? Just give introduction. Deepthi.
Yes, ma'am.
Yeah. You just introduce the resource person. That's it.
I consider it a great honor to welcome our chief guest, Dr. B. Dastagiri Reddy Garu. Welcome, sir.
Thank you, madam.
Yes, sir.
I hope you can see my screen.
Yes, sir. We can see that. Presentation is visible.
Okay, madam. I'm just waiting for it to load for the presentation. I think it's taking some time. Yeah. Good afternoon, everyone. Welcome once again. So we talked about properties of sun or the sunlight. Then we talked about semiconductors. So what are the semiconductors that are supposed to be used? And we covered that one. Now we'll be looking into solar PV cell. So how a cell works, and then we'll move to how these cells are converted into modules and arrays. Okay, so here is what my summary of this particular part of the presentation. So I talk about solar cell, then collection probability, quantum efficiency, photovoltaic effect, what does that mean? Then the IV curve, then the effects of resistance, radiation, and temperature on the IV curve. So we have seen PN junction under thermal equilibrium in the last session. So this is how it looks. So there'll be some diffusion, some drift of both electrons and holes, and finally it will settle down like this. Okay. And we have seen, I don't want to go through all these formulas. You may be knowing these things again. So when it comes to solar cell operation, there are basically 4 steps involved. Number one, you have to generate the light generated carriers. That means by using the photon energy available in the sunlight, you have to generate an electron hole pair. So that is what the light generated carriers. Okay. How to generate that one we have already seen. So there will be some energy in terms of electron volt, and that will be used for the electron to excite to the valency band to conduction band. We have seen that one. Okay. Now the second part that is very important is the collection of light generated carriers. So once it is generated, it's not the job done. You have to collect that one. You have to separate that one by using the energy barrier or the potential created within that. The electric field created within the junction, you should be able to collect them, or I would say you have to separate them first of all. Then once that is separated, then you end up in a new voltage. Basically, there is a band gap and there is some voltage available there. But once the separation happens, then there will be a new voltage coming across that particular junction. That is what called photovoltaic effect. Okay, anyway, we'll discuss that in a while. Now, the third part is you connect a load, external source, and you try to recombine the separated charge carriers again. So that's the 4 parts of the solar cell operation. So number one is you have to generate, then you have to separate, then because of separation, there will be some voltage, which is slightly different than the existing barrier voltage. Then you have to connect the load so that the light generated carriers recombine once again. Okay. So once the light is there, these yellow things are called lights. When light is there, you get lot of electron hole pairs on both sides. And because of the junction where you have some electric field, so you get separation. That is what going to happen. You get all it separated. Then there will be a new voltage coming up. So that is what actually pushing the electron to pass through the load. So when you connect something here in this path, so that's how you get a light generated current. So a better animation, a photon comes here, you generated electron hole pair, and you see the width of N junction and P junction. As I said, there will be collection probability. The collection probability will be more at the junction. So you have to construct the panel such that your junction is very close to the surface. So you see N is very small in terms of width, and P can be bigger one where the recombination happens. Okay. So once the light generates this electron hole pair, then the second part comes the separation. Okay. So the separation means because it is a hole in the N side, which can easily pass through the barrier potential, because there is E in the direction of N to P, and this hole is nothing but a positively charged thing we can consider. It can easily pass through the junction. The other guy, that is electron, it cannot pass through the junction, but it can pass through some external connection. Okay, so that's how you are able to generate, then separate. Okay, so once the separation is done, you pass through that one through the load, and it comes back and recombine here. Well, now there will be a lot of generation, light generation, carrier generation will be happening, but where exactly the generation should happen so that you can easily separate them. So this particular graph tells you where this generation should happen, and
So
if it
sorry to disturb
happens,
you, sir. So presentation is not
yes, ma'am.
visible, sir. PPTs
Okay,
are not visible.
actually, yeah, I'll start now. I hope it will show up in a minute. Is it showing up, madam?
Yes,
At
sir.
least loading.
Yeah, now it's visible, sir. Collection probability.
Yeah.
Yes, sir.
So as I said, generation is one part. The second part is collection. So you collect as many as possible so that the efficiency of the solar cell will be more. So for that, we have seen the difficulties in that. We cannot use a bigger N portion, bigger P portion, because there are so many constraints, light absorption, then this diffusion length, how this electron can travel for quite long without recombination. All these things come into picture here to decide the thickness of N layer and P layer. Okay. So, but from the studies, it shows that if it is at the junction, that it is, if the generation is happening at near the junction, that means, what does mean is, you have some electric force here. Okay, so if you are generating an electron hole pair here, one positive, one negative, then it can easily get attracted by this one, or it can easily push this positive away. But if it is somewhere far at the junction, somewhere here, so this electric field effect may not be that strong here, so that it cannot attract or it cannot separate the things. So that's quite obvious. So that is what we are proving here. Okay. So if it is near the potential or the field, then it is very easy to, but to make that one, construction is the difficult part. Okay. Theoretically, we can directly say that, okay, if you are near to the electric field, it is easy to separate. But practically, how to bring that one is a big challenge there. So that is where you have to compromise on the thickness of the material. Then if you compromise on the thickness, you are compromising on the number of cells or electrons or hole pairs that you can generate. And that's how you are limiting to the power level of the PV panel itself. But if your PV panel that is available is 300 watts only, single panel. Because these are all the reasons behind that, why you cannot generate a big panel within 300 or maybe 30 meters square or 1 meter square. So these and all the reasons behind that. So everything is a challenge. Okay, so at the junction, it will be more. If you are passing away from the junction, then it will be difficult for you. And we also seen that the generation is more at the surface. Okay, if your junction is near to the surface, then it is easy that you can get more efficiencies of PV panel, but unfortunately that is not possible. Okay, so you cannot have a very small N junction, N layer at the surface of the PV panel. So that's why definitely you have to compromise and go little beyond there, and you see the generation has stopped. If your junction is here, but people are working towards that one. One research that is going on is having a multiple layer junctions. I'm showing just one junction here. Then there will be another junction, another junction, another junction, so that everything will get collected here. Once there are multiple junction, what happens? Your curve will be like this, so that you can collect more number of junction 1. This is for junction 2, and this is for junction 3. So instead of going like this, the curve will be something like this. That's how you can get more efficiencies with a single panel. Okay. Now there is something called quantum efficiency. This is something related to the, again, the amount of energy associated with individual color of wavelength, that is blue color, red color, some blue to red. You can clearly see that the the energy available with the blue is high. So definitely the efficiency will be high. Efficiency in the sense whether you are able to utilize all the electron volt energy available in the photon or not. So that is what the simple definition I can give you. So the quantum efficiency of a silicon solar cell. Quantum efficiency is usually not measured much below 350 nanometers, because below 350 nanometers there is no there will be electron volt power will be very less. The photon energy will be very less, which you cannot utilize. Okay, so what is photovoltaic effect now? I think I already mentioned that one. So once there is light, there'll be so much new electrons and holes coming into picture. Then what happens? There will be moderate field. No? When light happens, there'll be more things will come into picture. Then be some exchange of electron diffusion and drift current. The moderate field has come down a smaller field. It has reduced a bit. Okay. Then the overall thing will come to again normal when you try to join the two terminals. Okay. So there will be basically there will be change in the potential across this particular junction. Okay, before light generated carriers and after light generated carriers, the amount of voltage will be differed because there will be so much collection of new electrons and protons. So there will be new voltage coming into picture. So that is what called photovoltaic effect. Then when you use that electric voltage, then you are able to transfer the current through the load. So that's how all your electrons tries to come here and goes to the load, and then finally it will recombines in the P junction. When it comes to the IV curve, actually it is something similar to diode curve. We all know this is the diode curve. And what happens here is when the light falls on it, it tries to push the IV curve into the fourth quadrant. Okay, so whenever there is a light here, it tries to push down. The curve tries to push down. Then more light, then it tries to push further. Okay, so but for our convenience, what we have done is we just inverted that one and showing that as an IV curve like this. Basically, it's a diode current, but it is not passing through the diode. It is not crossing the junction. It is outside the diode. Okay, it is passing through outside the diode. So that is why it will be going to the fourth quadrant of the diode characteristic, but we generally invert that one and show this as an IV curve. Okay, and these equations are quite straightforward. We know this diode equation, diode current, that is I naught into e power QE by NKT minus 1. But here there is one more current coming into picture, that is called a light generated current. This is because of light, that is the photons falling on the surface of the PV panel, then generation of new carriers, then the separation, and that separation generates a new voltage, and that new voltage is making the electrons to flow outside the diode, but not inside the diode, outside the diode. So that is why there will be another current coming into picture, that is called IL, light generated carriers. Okay, but if you do some mathematics, finally you will get you can neglect this minus 1 because obviously this will be quite high, and the total current will be the light generated current minus the diode current. The diode current is happening because of the diffusion. It can be electron diffusion or hole diffusion. So basically, which is directly passing through the junction is diffusion currents. But the drift current is more here. The drift current is light generated current. The drift current is nothing but the current which is passing through the load, which is not following passing through the junction, which is passing outside the junction. So that is what IL here. So the light generated current minus the diffusion currents, that is nothing but the diode current. That is how your current equation of a PV panel look like. Okay. So then what is short circuit current? That is very simple. So if there is no what to say, it is quite straightforward. I don't need to explain too much about short circuit current. So it will be the maximum current when you directly short circuit the PN junction. This will be the current, and this will be the open circuit voltage. Okay. So when you don't connect anything, after the light generated carriers are getting separated, then you see certain voltage. So that will be reflected as open circuit voltage. And the curve, I already explained, it is supposed to be a diode current in fourth quadrant, but for our convenience, we just shifted that one to the upside down. Okay, I think again the screen has gone. I'll go back and share it again. Madam, is my screen still visible?
Yes, sir. Yes, sir. Visible, sir.
Okay. Okay, madam. So the short circuit current depends on multiple factors which are listed here. So this result in the area of the solar cell. We know why it is, because if more the area, more the generation, and more the number of photons. How much photons you receive, that is also reflecting in the number of electron hole pair generation. Okay. And also the optical properties. Optical properties like solar panel, if you see, there is no direct exposure of junction there. So there will be some extra glass covering the surface. If you closely look that one, so there'll be extra layer covering that one just to protect from physical damages. So that may reflect some of the light incident on the solar panel. So that is also affecting the short circuit current. And also the collection probability, as I said, the collection probability will be more if the electron hole pairs are generated next to the junction, but unfortunately that is not happening because of practical issues, practical reasons, because you cannot reduce the thickness of n layer. So that is why there will be some issues with the collection probability. So these are all the factors that is affecting the short circuit current. Well, the short circuit current also depends on irradiance. That we have already seen. What is this air mass 1.5 or 1.0? If it is AM0, then it would have been much better. But unfortunately, we don't receive such kind of irradiation. Now, when it comes to open circuit voltage, there are some factors affecting that one. That is quite straightforward. What is the junction you selected? Okay, we already discussed about what is the trade-off that will be there when you define the junction voltage of a diode. When you select selection of semiconductor itself, we have taken this step. We compromised on the voltage. If it is a bigger voltage, then there will be less current. So obviously we have compromised on that one, and that is why there will be a restriction with respect to the cell voltage. So always the cell voltage, if you look at it, will be around 0.5, 0.3, 0.6. It will be varying only this range. So that's the reason we cannot go bigger voltages for individual cell voltage. So these cell voltage connected in series and parallel, that's how you get the total amount of current or power rating of the PV panel. So basically, I'm trying to cover what we know, but putting a why there. Why cell voltage is not higher than 0.5? Why not cell voltage can be 2 volt, so that if I have 10 cells in series, then it will be like higher voltage, 20 volt. So if you ask me why, these are the answers. So for every concept, what I'm covering in this full session is putting a why to everything. Why this, why this, why this. So if you ask me why, these are the answers. So that's how I prepared the presentation. But few things may be quite obvious to most of the participants because all are faculty, so they might have known all these things. But I'm just giving the practical considerations and challenges in varying these things. For example, if you ask me short circuit current, why cannot you vary? Because there are these things issues. Because the collection probability, the thickness of N material, the thickness of P type, N type, then the junction. Then if you why can't you increase the open circuit voltage? So these and all the reasons behind that one. Fine. Now, when it comes to fill factor, so fill factor is nothing but the ratio of what is the maximum power that you can generate by to the short circuit current into open circuit voltage. Okay, so there will be different panels available out there in the market. So you have to be very careful in looking at this particular factor called fill factor. Okay, you can see just if you rely on open maximum and open circuit voltage, if the difference is not much, then it is a good panel. If there is a huge difference between open circuit voltage and VMP or ISC, then that is not a good panel, because the fill factor is nothing but it tells you what is the maximum it can give, but what is the VSC. If the VSC is very high and if the VMP is very small, then there is an issue with the fill factor. Okay, so you have to be very careful in selecting the PV panel. If the fill factor is very less, you see only you can generate this much, but it is capable of generating this much. Okay, so roughly most of the commercial PV panels are around 0.7 or 0.8 fill factor, 0.77 exactly. But most of the PV panels will be somewhere around that value. If it is less than 0.5, then my suggestion is not to go with that particular panel. There are multiple panels available out there in the market, and which has different issues with that one. So you have to be very careful in selecting the PV panel. Fine. Now we'll see about solar efficiency. So we talked about many things now. So everything is important. Everything is considered for the efficiency. If you see the efficiency of PV panel, you can see fill factor is one of the consideration. It is directly proportional to your efficiency. Okay. open circuit voltage, short circuit current, and fill factor divided by P in. What is P in? It is the input energy that you are getting through light. Okay. And we have seen efficiencies of different PV panels in the very beginning of the PPT. For multi-junctions, it will be around 46%. For uni-junction, it will be around 24 or 23%. And there are some other cells like die cells, it will be much less as well. Okay, the input power can be calculated like this. So if it is the input efficiency calculation is 1 kilowatt per meter square or 100 milliwatt per centimeter square. That's the input power. So based on that, you can calculate the input power. Okay. And I've just given you a simple calculation which shows the efficiency is 14.96. Okay, tandem of cells. What is the tandem of cells? I hope you can recall what I said in the morning session. So when there is a incoming spectrum coming with all the lights, then you can have a high band gap cell which can utilize the blue. What is the amount that you have here is it varies from 3 electron volt to 1.7 electron volt. Of course, there will be some losses in between. It may be uh, slightly less than 3. So you can use one uh, junction which will be utilizing this particular light, blue light, then the rest will be passing through without doing anything. So in that case, what you can do is you can come up with one more junction which can utilize the rest of the light. So that's how you can make these two in series so that you can get a better cell voltage or better short circuit. If you connect in parallel, better short circuit current or a better open circuit voltage. So that's how. But again, you have to think about all the aspects. Like I said, even for one junction, the thickness will be in micrometers. If you are going for multiple junctions, then you have to think about how much you have to worry about the thickness of the PV panels, then this diffusion length, then also what is this collection probability, everything. So it is very, very tough to come up with a multi-junction thing. So there is a huge research going on around this. So if you, there is one study says that if you increase the junctions, the solar panel efficiency can go as high as 60. Okay. Yeah. Now let's look at some important parameter called characteristic resistance. I hope we all know about this thing, but just to have a quick look at it. So characteristic resistance curve which is shown here, which will be a ratio of VMP by IMP, okay, or also VSC by ISC. Okay. So if the resistance of the load is equal to the characteristic impedance of the solar cell, then the maximum power will be transferred to the load. It is quite obvious about we all studied this maximum power transfer theorem. Okay. And when it comes to MPPT, what you are doing is you are trying to adjust this characteristic impedance by utilizing a DC-DC converter. So that is what you are doing with MPPT techniques. Basically, you are trying to adjust the impedance of the total system. Okay. So that's how MPPT works. Fine. Now, when it comes to equivalent circuit, we'll see in detail what is why series resistance comes into picture. Okay. So why series resistance comes into picture? Because the movement of current through emitter and base of the solar cell. So all the currents has to move in certain paths. Okay, and the contact resistances, whatever if you want to collect everything, if you look at PV panel carefully, there will be one aluminum or white color thing going across all the PV panels. So all these contacts will come into picture before passing it through the load. So your load will be somewhere here, right? So the total current has to pass through many things. So that is why there will be a series resistance to be included. Again, there might be some interruption in the PPT. I'm sharing it again. Okay, I hope the screen is visible to you.
Yes, yes, sir. Visible, sir.
Yeah. So how it affects the equivalent circuit. So we know that we have seen that the total current is light generated current minus diode current. But because of the series resistance, how it happens, there will be some drop here. Instead of QV, you will see as V plus IRS. So that's how the equivalent or the current equation changes. Now, when it comes to parallel resistance, that is shunt resistance, this is also quite straightforward because it is difficult due to the difficulties or manufacturing defects and also represents the recombination losses. We also discussed this one. So whenever there is a collection of, whenever there is a generation of 10 to the power of 23 electron hole pairs, you may not be able to collect everything because it may not be near to the junction. So for that, there will be some current you are losing. That is nothing but the shunt resistance that reflected in the shunt resistance. And because of that, what happens? It is some current going away from the total current. So it should be minus V by RSH. So this was the equation we come across. That is the total current is light generated current minus diode current. So diode current is because of some diffusion happening between the junctions. Okay. And this has changed to V plus IRS because of series resistance. And one more term comes into picture because it represents the recombination losses. So that's how your equation has took this particular shape. So to represent a total equivalent circuit, it will be like this. If there are multiple junctions, then you have to go with a different model. Okay, I hope you all aware of that one. Okay. So finally, this will be the resultant current equation, which is shown here. Okay, now what is the effect of RS and RSH separately? So the series resistance has greater effect on high intensity, performance at high intensity. Okay, if the series resistance is more, it has impact on high intensity. High intensity in when you have a more current coming into picture, the series resistance is more, then there will be a drop. So I square R losses will come into picture. What about shunt one? It will be having a less performance at the low intensity. So low intensity means there will be already low current. In that, some losses is happening. So the most of the current goes to the shunt part. So it is clearly shown from this. So when I change the resistance, series resistance, this is how your curve varies. And similarly, when you change the shunt, this is how your curve varies. So the series resistance has huge impact when the irradiance is quite high. The shunt resistance has greater effect when the irradiance is very low. Okay, so that's how the shape of IV curve changes with the effect of series resistance changing and when shunt resistance is changing. Fine. What about the effect of temperature? Okay, so again, with the temperature, there may be a rise in current because we know that electrons can excite with the temperature. So obviously there may be an increase in current, but we also seen that with the rise in temperature, the band gap reduces. That means the voltage will come down. That's exactly shown here. So if the temperature is more, the current may be more, but the voltage will come down. So basically it will affect, somehow it affect the power. And when you are installing PV panels at your locations, at your premises, then make sure there is certain uh, distance between the panel and the height you are fixing. So there should be proper airflow so that the temperature won't go beyond the given condition. You might have seen that in the panel it says standard testing condition is irradiance 1000 watt per meter square and AM 1.5, the temperature is 25 degrees. So if the temperature is different from that, there will be a change in the values that you are looking at. Okay, so but what will be the effect is very simple. With the temperature, you can excite more electrons, so there will be more current. But with the temperature, the junction voltage comes down. That's quite obvious. So that is the reason you get there will be a little alteration between voltage. So VOC decreases, ISC little increase. So that's how the curve changes like this. Okay, and this is the equation that will be reflected in the change of temperature. This we ran some simulation just to show you how this IV curve varies with respect to intensity and irradiance. So for example, if the irradiance is good, then the curve it will be like this. If the reduces, it is like pushing the curve down. That's it. Okay, you push the curve down. That is what reflecting in the change of irradiation. Just pushing the curve down, the diode current. Okay. So next we'll look at modules and arrays. How to make this solar cell become as a module and what will be the issues with that one or the challenges that we will be facing with that one. Madam, any questions so far in the chat? Or...
No, sir. No more questions here.
Okay.
Yes.
So basically, solar cell works with four steps: generation of light generation carriers, that is holes and electrons. Then second step, you have to collect them, that is by utilizing the electric field available with you inside the PN junction. Then you have to, because of this separation, there will be a different voltage coming into picture. Then when you connect the any load across the junction, the current will pass through outside the junction. Okay, so we are talking about the current which is not flowing through the junction, but it is outside the junction. Now let's have a look at photovoltaic technology in last part of this one, that is modules and arrays. Okay. So I'll talk about cell to module, series parallel connection, what happens if there is a mismatch, what happens if there is a shading effect, then what is this bypass diodes and blocking diodes that you might have come across. Okay. So cell to module, this is a cell we talked about so far. It will be roughly around 0.5 and 1 ampere, something like this. Okay, it won't be too much huge voltage, but current may be somewhere around 1 ampere or 1.2 ampere. So that will be the rating of a single cell. And we have come across what are the issues in extending or expecting a bigger values of cell voltage and cell current. We have also looked at that. Okay, and when you connect all these things, go and this line, that is what I was talking about, the collection thing. Finally, all the things has to be collected here and it will be joining all the cells, this particular white lines. Okay? There is a connection. This is also considered in PV panel modeling by considering as series resistance. Okay? All these connections will come into series resistance. Okay? And it's a module and array. Okay? I think it is self-explanatory. We don't have to look deeper inside that. Okay, so far, to my knowledge, I mean, in the internet, what I see is this is the biggest panel we have available. So that is from Panasonic N330 or N325. That's the model number. It's around 330 watt. Okay, that's the biggest panel so far. Now, when it comes to module circuit design, it is very simple. You have one cell of 0.5 volt or 0.6 volt and 1 ampere. So if you want to make it 12 volt, it is obvious you have to connect them in series. If you want to make more current, then you have to connect them in parallel. So that's quite straightforward. No need to have too much discussion about that one. But when you do that, what happens to your total current equation it will be changing like this. You have to just give some multiplication factors, that is M and N. It's quite straightforward. I don't want to go too much details about that one because it's quite easy. But what is important is what if there is a mismatch? Okay. So we also have studied this mismatch in diodes, but here it is something different because you have one diode which is already there inside, but the current will be passing outside. So there will be some impact whenever there is a mismatch. We'll see that one. So basically, if nothing is wrong, then you add up two voltages. If something is wrong, then the result will be the reduced voltage. That, in simple words, that's what we can say. Okay, as two cells are connected in series, the current through the solar cell is same, and the voltage is found to be adding in particular current. So the same current, it will be adding. So that's simple. So whenever there is a mismatch, then what happens? Okay. So at this point, there is mismatch. What happens is there will be some current dissipated in the poor cell. So that is what the impact in mismatch in current when connected in series. When you are connected in series, if the current is same, no issue. If the current is not same, then what happens? The whatever may be the difference in the current will reflect as the dissipation power. I mean, whichever the diode or whichever the PV cell is getting less current, the difference current will be dissipated in that cell itself. So there will be high power dissipation in the poor cell. Okay, we'll see more details in a while with one example, one calculated part. Okay, so this is how it works. So if the currents are matched, then you see these junctions is nothing happening. Okay, so whenever there is a mismatch, then what happens? This diode will start conducting and it will dissipate some energy here itself. Okay, so for example, if there are like 12 cells connected in series, each one of 0.5 volt, there will be 6 volt. If one solar cell gets affected, then what happens? Whatever may be the power generated by rest of the 5 will be dissipated in the fifth cell, the sixth cell, which is not doing well. Okay, then this will get damaged. So eventually the series connection gets disturbed. So there won't be any current path in that particular circuit. Okay, that's how even a single cell damage will result to the entire damage of the total cell. Okay, that's about series connection. When it comes to parallel connection, it is also something straightforward. We don't have any issues. If there is a difference in current, it will just add up. For example, if I1 and I2 are same, it will add up. If it is not same also, it's fine. But if there is a difference in voltage, then we know obviously that there will be some impact in that. Okay. So whenever there is a mismatch in the voltage when cells are connected in parallel, again same thing happens. So the difference in the voltage will be appeared across that particular cell, which may again forward bias the internal diode. Okay. Now what happens to the shading? So if the shading happens, let's run through this one. You can see the total curve try to shift down. That is what is going to happen with shading. So whenever there is a shift in the curve, then whether it is matching to the next cell or not, so that's how these things will come into picture. Okay, so now let us take this example. We have 10 cells connected in series, but one cell is partially shaded. So what happens from our previous discussion, what happens? Whatever may be the power generated by these 9 cells will be dissipating in this shaded cell. Okay, for example, if this generates like 40 watts, this 40 watts will be dissipating in this cell. It is not coming out of the panel. So this will definitely eventually damage this solar cell. Once it is damaged, then the series connection is entirely disturbed. So you cannot use that panel anymore. Okay. So this is how there is a large amount of power will be dissipated in the shaded cell. If you want to calculate something, let's take some example. And these are just get a mathematical expression how you get this one. So I'm not going into that details, but directly I'll show you what is the physics of shading and what happens exactly when one cell shaded. Okay, so this maybe give you a better idea. So a 36 cell PV module described has parallel resistance RP, so 6.6, series resistance 0.005, which is very less, that is good, under full sun. Under some load, the current is 2.14 ampere, that's the load, and the voltage is 19.41. If one cell is fully shaded, then the current somehow stays the same. Okay, then what would be the new module output voltage and power? What would be the voltage drop across the shaded cell? How the power would be dissipated in the shaded cell? Okay, so if you look at the answer, you'll see that the new voltage, see it has dropped down from 14.6 4.66 volt to 4.75 just because of one shaded shell. Okay. So there'll be huge difference in the voltage. The voltage drop across the shaded part will be 14.4. It's a huge voltage drop, which will make that diode forward bias and it is try to conduct itself. So the power dissipated will be 30.2 watts out of, if I'm not wrong, it is 20 volt, roughly 20 volt into 2 volt, 40 watts. Out of 40 watts, 30 watts are dissipated in that damaged cell or partially shaded cell, and that will eventually damage the entire cell. And once the one cell is completely damaged, definitely you may not be able to use that panel anymore. Okay? That's the impact of partial shading with one cell when cells are connected in series. Now, there is a huge issue, but there is a solution as well, that is with bypass diode. Okay. So what this bypass diode means, you have to connect a diode in parallel to that one. Under normal operating condition, your current will obviously flow through this one. Whenever there is an issue, then this diode will directly bypass this particular cell. Then you will be safe. For example, if you are having the same issue, what happens? Instead of forward biasing the internal diode, which will dissipate the energy here itself, by selecting appropriate diode with proper forward bias voltage, which will be less than this one, before the internal diode should turn on, this external diode should turn on. Okay, if it is delayed, then obviously the same thing is going to happen. So you have to select properly the diode. Then it may happen that whatever the power that is contributing by this particular cell may be bypassed, but still you are able to safeguard the entire panel. Okay. Now, in practical scenario, will you be getting bypass diodes for every cell? The answer is no, because it is very expensive. So mostly what they do is for half series elements, if there are 9, then for 4, there will be one bypass diode, or most of the panels you get only one for one parallel thing, one series thing. For any one tries to shade it, then everything will get bypassed. All the working panels also will get bypassed. So there'll be cost involved, too much of cost involved. So that's how you don't go for too many bypass diodes, but you may get uh, one for every series connection. Okay. So the series connected solar cell with bypass diodes, without bypass diodes. So how it happens? It is very simple, as shown in the previous figure. This just an animation showing you how the currents flows. Okay. So there will be, if there is no problem, then all the light generated currents will be circulating like this. If there is a problem, then this diode comes into picture, but the contribution of this particular guy will come down. The total current may come down, but there is no issue in damaging the entire PV panel. Okay, that's about bypass diode. And let's see with bypass diode and without bypass diode, what will be the power dissipation. Okay, I'm sorry, let this continue. So whenever there is a mismatch without bypass diode, we have seen that there will be a huge power dissipated in one of the cell. So there will be huge power, which will be so this much power will be dissipated in the shaded shell. But when there is a bypass diode, what happens? This curve, which was like this, is modified like this. And hence there will be very less power dissipated, and this will be in the bypass diode, not on the PV panel diode. There will be very less power, which will be in the bypass diode, which is capable of handling that low power. Okay. So this is to summarize. When you have a bypass diode, when you don't have a bypass diode, it will eventually damage the entire PV panel. When you have a bypass diode, there will be some power dissipated, which will be in the bypass diode and which it is capable of handling. Fine. So in the real world, as I said, for every 4, there will be one bypass diode, or most of the times I have seen it will be one diode for 8 or 9 cells together. So if one is shaded, then you get everything is bypassed. Okay, and that is also huge impact in the power that you are getting. You are not damaging, but the amount of power that you will be getting is very less because you are bypassing most of the healthy solar cells. But there is some research in connection. Instead of connecting like this, if you connect in a different way, instead of connecting all in series, but a panel, a position of cells in different locations and connecting them by using some logics, then there are some research papers showing that you don't have to rely on bypass diodes, but you can get rid of the effect of partial shading condition. There is a lot of papers available in partial shading conditions as well, and you can also explore those things. Okay. Basically, if there is a bypass diode, you will see a box something like this. When you open, you will find something like this. So that shows there is a bypass diode available there. So if there are 4 parallel strings, then you will see 4. If you see 8, then that's very good panel, but it will be expensive. Okay, so what about blocking diode? So blocking diode in simple concept, it is very easy. Okay, for example, you have 10 volt, 10 volt, 10 volt, all 10 volts, then no issue. But if one is 5 volt, then rest of the parallel are 10 volts. Then obviously this 5 volt guy will be in trouble. Okay, so there will be some reverse current flowing through them through that. So to block that one, generally it comes with the blocking diode. Very simple of that. So you can be 4 things, 4 diodes for 4, whatever may be the number of series connections available, you can have that many number of diodes. Okay, so overall, this is how your PV module or array looks like with bypass diodes and blocking diodes. Mostly only one blocking diode for entire panel. That is what in the real world. You cannot have one diode for every series section in a PV panel. Mostly it will be like these two will be connected in series and the rest two will be connected in series and the two batches will be connected in parallel. So one bypass diode for this set of 18 cells, then another set of bypass diode for another 18 cells, and there will be one blocking diode. So this is what you get in the real world. So you won't get blocking diodes for every bypass diode for every cell and also blocking diode for every series connection. Okay, we have to accept that one because there is too much cost involved, and also see all these diodes and everything has to come with a connection. And we know what is the significance of series resistance. Whenever there is a blocking diode, your cell voltage itself is zero point 0.5 and everything add up together, then you are reducing some voltage because of the diode. So either you have to go for a very good diode, which will be super expensive, so that you won't get a drop in the panel voltage. Okay. So if anyone is issue, then you would bypass the entire panel. That is what happening most of the cases. Okay, so that's about PV panels, basics of PV panels. And if there are any questions, we can take it now. If not, I'll try to continue with some of the grid connection issues. Basically, that's my part from PV panel basics.
Sir, we can continue with the grid connection, sir. Sir, because no one has posted. Sir, one question. At what time bypass diodes are activated?
Okay, whenever there is a mismatch in the current produced by the series connected panel, then for example, this is generating 2 ampere, this is generating 1 ampere, then there will be an issue. So definitely it will activate the bypass diode because there will be a reverse voltage applied across this particular solar cell. So it tries to act as a load for all these cells. So before that happen, the bypass diode will get activated. Whenever there is a reverse voltage applied, then that will be a forward bias voltage for this bypass diode. Basically, in other words, you can say whenever there is a forward voltage applied across the bypass diode, it will get activated.
One more question, sir. Any research opportunities with respect to PV cell?
Yeah, PV cell is huge research is going on when it comes to selection of components, then utilizing multi junctions, then the thickness, how to address the thickness, how to address the diffusion lengths of electrons and holes. Is there any way? And also how to effectively utilize the entire spectrum range that is also there. And there'll be one more research going on with arrangement of PV panels, how to arrange the PV panels in a different way so that you can get rid of all these partial shading effects and also the space that you are supposed to utilize. Instead of putting the panels everything on the floor ground, why can't you arrange them as a tree? Like if you look at the biology of the tree, every leaf gets equal amount of irradiation, though it looks like it is a bunch of leaves, but every leaf gets equal irradiance. So it somehow steady that one or arrange the PV panel in such a way that you reduce the space requirements of PV panel installation.
Sir,
And
uh,
depends on the location. Yeah, yes, please.
so one more question, sir. Is there manufacturing of PV cells in India?
I'm not sure, but I don't think it's there in India.
Yes. Sir, again, same question. PhD research topics they are asking. And one more question: how to minimize multiple peaks due to bypass diodes?
Uh, See, from the basics of PV panel, we understood that without bypass diode, you will eventually damage the PV panel. Okay, so you have to accept the multiple peaks. Otherwise, there won't be PV panel without these blocking diodes or bypass diodes. So that is where your MPPT techniques will come into picture. We have also, unfortunately, I may not have the results of the multiple peaks. We simulated like when a bird flies, how this impact when a cloud pass over with one of the portion of the PV panel. So we get uh, quite interesting multiple peaks. Okay, because of with blocking diodes, without blocking diodes, there will be multiple peaks. You have to accept that one. So there is no way that you can get rid of these peaks. If you want to avoid, then you may eventually damage the PV panel.
Sir, other than bypass diode, any other option available?
To my knowledge, there is no other option. Maybe you can come up with something new, maybe a less cost thing. Basically, industry works with techno-economic evaluation. Though your technology is very good, but if it is super expensive, no one is going to take your solution.
Yes, sir. Sir, participants, you are having any questions? Sir will proceed with the integrated grid. If you are not having any questions, Sir will proceed with the next topic.
Not next topic is not a big topic. Maybe I'll just give an overview of how this grid connection thing
Yes, sir.
works.
Sir, we'll proceed with the next, sir. Sir.
Okay, so
Okay.
basically, okay, I'll do one thing. I'll just give you some direction of how grid integration works, and then we can close the session. Okay, basically there are uh, three types of grids that you can think of. So the main grid, so that is strong grid, and there is something called and there is weak grid. So what is strong grid is ideal voltage source. We can take that as an ideal voltage source. So we know the definition of ideal voltage source. That is, irrespective of whatever you connect as a load, I don't care. I generally gives you the same voltage. You take any load, linear load or non-linear load, or whatever maybe the loads that are available, you can take it. But I always give you same voltage and frequency. So it's voltage, magnitude, frequency, and theta cannot be disturbed. I mean, you cannot disturb if it is a strong grid. Okay. Now, when it comes to the smart guy, which is basically a voltage source converter. Okay. So it is VSC. With VSC, what you can do is you can change the magnitude, you can change the frequency, and you can change the theta. Okay. So that is why it is called as smart guy. So you can do many things. Okay. With proper control, you can ask this VSC to follow this. You get using PLL, you get this voltage, frequency, and theta reference, and you can ask this guy to follow that one because you are capable of varying your voltage, frequency, and theta. So you can follow that one actually. So that is like grid following mode. And you can also do grid forming mode. But you can have closed loop control of your own output voltage, output frequency, and you can maintain this voltage and frequency. That is what called grid forming mode. Okay. Now there is another version of utilizing the voltage source converter, that is grid supporting mode. So what is grid supporting mode? You know how to follow and you know how to form your own grid. But if there is something in between, is that possibility? Is that requirement? Yes, the answer is yes. There is a possibility that you can utilize for multiple purpose. And one such scenario is grid supporting mode. So I will try to explain this one. What is this grid supporting mode in a while? Before that, let's have a look at the other guy. That is, let's take a different color. It's a V grid. So V grid is something like a voltage source again, but its voltage is dependent on multiple factors because of its series impedance. Okay. So basically, you represent this guy as a resistance and inductance. So this is how you represent this guy. So what happens is whenever there is a load, if there is a nonlinear load or a variable load, it depends on the load. What happens if your voltage here is sine wave, and if you draw a nonlinear current, there will be nonlinear drop across this impedance. So what you see at this location will be quite different. So it will be like based on the load. It depends on the load. If it is resistive, you get something like this. If it is nonlinear load, then you get disturbed voltage at this point. Okay. So that is what called V grid, or in simple terms, we say which is having a huge impedance in series with the source. Okay. Or short circuit ratio, less short circuit ratio, less short circuit capability. Okay. Now, when in theory, like in simulations, in most of the papers, you see that either you consider a strong grid and you try to connect the PV panel to the grid, but you will never consider connecting a PV panel to a V grid. Okay. So if you're thinking about PV integration to grid, so I suggest go with this interaction, smart grid to V grid. Or if you say this one like voltage source converter connected to strong grid, it is quite straightforward. You cannot change this voltage, frequency, and theta, whatever may be the load. Whether you connect something, take power, or if you want to inject power, no issues with that one. You can always do that one. So, but most of the research is saturated in this range from interaction of these two. It is almost saturated. Nothing is there to figure out. Maybe I am seeing some papers, like personally, I see that instead of two-level inverter, they go with three-level inverter, they go with a multi-level inverter, and they say that it is quite good in performance, but I feel it's not a good idea. At the end of the day, it is a voltage source converter, whether it is multi-level or two-level, it is a voltage source converter. It's follows the same principle. So there is no need to do too much of research in that. Just replacing a two-level converter with a multi-level converter or three-level converter. There may be some additional things, but it is already explored and it is already published. But Very few papers are there when it comes to interaction of these two. Okay, the smart grid and a V grid. In some cases, all the three. Okay, so let's take that scenario. All the three are available. Okay, let's say all the three are available. What happens there? Okay, let me clear this and draw it once again. Okay, so we are talking about smart grid, strong grid. This is a strong guy, smart, and weak. So we know that in grid following mode, okay, you can rely on PLL. So you get V, F, theta, and you can make this voltage source converter to get that one. But let us assume there is a scenario. You are the only source available. I mean, I'm talking about the voltage source converter. You are the only source available, and you are feeding a local load. Okay. Now, the strong grid comes into picture, and you want to integrate this one to this. So my question to participants is, can you simply rely on PLL when you are already feeding a load? Any question, any answers? When you are when the converter is already feeding a load, and now you want to switch over to grid forming mode from grid following mode. I mean, grid, you are the one maintaining the voltage and frequency and feeding a load, and now suddenly grid comes into picture and you want to go and join the existing grid. Simple PLL is more than enough or not enough, or what is that problem that you get if you rely on single PLL? Okay. So what happens is, for example, you are feeding the load with certain voltage, frequency, and theta, but the red color waveform may be, let's say, something like this at the time of turning on PLL. So what happens? There is a huge jump here. There is a huge change in theta, and also there is, instead of at this point, instead of maximum value, it is going to minimum value, but in negative half cycle, instead of minus thing, it is coming to 0. So there will be a huge difference in magnitudes, V magnitude, and also theta. So I hope you all know what happens if there is a huge difference in voltages and theta. At that point of time, when the PLL tries to turn on and try to synchronize, you will see a huge jump in the voltages and theta that will result in huge exchange of currents between these two guys, and it eventually trip the converter, saying that overcurrent. That is what happens. But there is a possibility, by theory of probability, when you turn on PLL, you may get the voltage which is exactly same like this. It's a probability. Okay. So the issue is, if the converter is already feeding a load, and if you want to go and synchronize to a grid, then there will be an issue. So you cannot simply rely on your PLL. Okay. So that is one thing. And also we need to have a keep in mind that in strong grid, that is a voltage source and without any resistance, or very maybe a small inductance and small capacitance, here your active power depends on theta variations, and your reactive power Q depends on voltage magnitude. But in converter case, whose equivalent circuit will be, one second, let me clear this. In converter case, The equivalent circuit is voltage in series with resistance. Okay, if you look at any paper, how they model a voltage source converter is voltage source in series with the resistance, but not with inductance. Okay, I hope you all know why. Because there is no inductance part in the voltage source converter. It's only the drop across each switch, which is a resistance drop. So it is a resistive based network. But when it comes to weak network, the equivalent circuit is big inductance, big resistance. Okay. So here the relation is like this, but when it comes to converter, the relation is both P and Q linked to V magnitude alone. Okay. And here it depends on which is bigger, whether your in L or XL is dominating or your R is dominating. So it depends on that one. So that's how the relation varies. In what way P is linked, whether P is linked to magnitude or the theta or frequency indirectly. Okay. So if you integrate theta, if you integrate frequency, you get theta. So whether it is linked to frequency or whether it is linked to voltage alone. So because of these three uh, categories of these three characteristics of the grids, when you're dealing with grid integration or interacting two or three more grids, which is of different characteristics in the sense which is strong, weak, and smart, you have to be very careful in deciding the droop characteristics, in designing the droop characteristics or designing the control loops. So, for example, if you are dealing with this guy, and if there is a change in power, if you keep on varying frequency, it may not work out. You have to see what is the actual relation, and then you have to accordingly tune which one you have to rely on, which is the factor that will be affecting the power, which will be the factor that will be affecting reactive power. So in that way, you have to decide your control strategy. So there are different modes and different mode transitions. If you want to look for mode in the sense like you are already connected and working together. Mode transition is you want to change from one mode to another mode. Grid forming mode to grid supporting mode. Grid supporting mode to grid following mode. So there are different modes available out there and different sources. If it is a PV, you can take that as still a resistance based network. Of course, if you don't have a transformer after the PV converter. So based on that, you need to decide what is your equivalent circuit, then you have to go with the appropriate control or a better controller that can takes care of all these differences. So that's the overall view that I want to give about grid integration. Yeah, any questions or any other topic,
నెట్లో ఒకసారి షేర్
anything that
చేసావా?
participant would like
సేవ్
to
చేసి
discuss?
ఆ సేవ్ చేసిన దాన్ని డ్రైవ్లోకి వెళ్ళి రైట్ క్లిక్ ఇచ్చామంటే అప్లోడ్ ఫైల్ అని వస్తుంది. ఏదైతే చేసావో దాన్ని అప్లోడ్ చేయమని.
Madam, I hope I'm still audible.
ఎస్ సార్, ఎస్ సార్. సార్
Yes, madam. Any question, madam?
నో సార్, nobody has posted the questions.
Okay. Okay. Okay, madam. Still, we have around 30 minutes or more than 30 minutes. So if there is a discussion, then I'm open here.
Sir, 5 minutes, sir.
Okay, madam.
Banu, actually, sir, లేరా? పేరు హెచ్ఓడి సార్. సార్ సెషన్ అయిపోయింది. సార్ చెప్పేశారు అంతా. జాయిన్ అయ్యి ఓట్ ఆఫ్ థ్యాంక్స్ చెప్పేస్తే అయిపోతుంది సార్. క్వైరీస్ ఏం రాలేదు సార్, వచ్చినవి మధ్యలోనే అడిగారు సార్, అప్పుడే చదివేశాను. I request all the participants, if you are having any queries, you can unmute yourself and you can ask the resource person.
Madam, are there any participants from other states?
Yes, sir, they are.
Mostly from Andhra.
No, sir, they are from other states also there, sir. Maharashtra and there. Maharashtra and there also they are coming from, sir.
Okay.
One request to participants, please, all of you, please switch on your videos so that we can take one snap and for proof. Thank you, all of you. If anyone wants to interact with the resource person, they can join. I request HOD sir to give the vote of thanks to the resource persons.
Thank you, Sunita ma'am. Am I audible, ma'am?
Yes, sir.
Yes, sir.
Yes. Sir, thank you, participants, for your patience. From SC College of Engineering Management and on behalf of our committee members, I personally thank Dasagiri sir for, first of all, agreeing within a short span. So actually, we thought of only one session, but later we have gone through the profile and we requested personally to take up the 2 sessions. So, sir immediately accepted this. So for that, I'm very much thankful to you, sir. Thank you so much for agreeing first. And today is a very special day for you. Even though you agreed for attending, delivering a session, the two sessions, I understand that. But thank you so much, sir. We are for this kindness. And all the participants who participated these sessions, I really thank for your patience. And the committee members.
Sir,
Yeah.
any feedback link?
Yeah, please hold for a few seconds. We will. Yes, sir. We are about to post, sir.
So
Please just hold for a
just
few
now we have
seconds, sir.
posted, sir. Feedback link is posted with the quiz also there.
Yes.
How to see, madam? In this? in this
Chat box.
platform, how to see
Chat
this
box
one
is
feedback from?
chat box is there, sir. Chat box.
Where is chat box?
Sir,
I'm not getting chat box. Where is I'm not
sir,
getting madam chat box.
uh,
That's why I'm asking.
sir, just in your
Sir,
Google Meet, if you just see your, sir, whether
sir,
you are using mobile or laptop, sir. Hello,
sir,
sir,
sir.
Narendra, sir, are you using mobile or laptop, sir?
Mobile, sir.
Sir, in your mobile, if you just
Mobile.
touch your screen, yes, sir, there will be three symbols, sir.
Okay.
One is participants count will be there. Beside that,
Yeah.
there is a one
Yes, sir.
circle shape symbol is there. Click on it, sir.
Yes, sir.
You will be able to see a chart box. This is a chart box, sir. You can click on the HTTP link, sir. You
In
can
call
fill it, sir.
message, sir. In call message, sir. Sir.
No, sir. This
Hello.
Yes,
in
yes,
your
yes,
Google Meet
yes,
itself.
yes. No, no, yes, in call messages.
In call
In call.
messages.
This
Yes, sir.
is in call messages.
Yes.
Yes.
Oh, okay, sir. I am getting, sir. Thank you, sir. Thanks. Thanks.
Okay, sir. Yeah. Sir, Dasgir, sir, sorry for the disturbance. Once again, thank you, sir.
No problem, sir. And
Thank you so much, sir, for coming and agreeing for this event, sir. In future also, I expect your kind support for our future events also, sir.
Sure, sir. Anytime, sir. And I would
Sir.
like to thank participants as well. I know it's very basic level of presentation because that's what the FTP demands. You start with very basics and then go to the research sessions. So that's the reason behind going very basic level of PV presentation. I hope I did not fail you bore like.
Exactly, sir.
Sometimes
What we planned. Yes,
yeah.
sir.
Yeah, so as per the plan, I was supposed to take the very basic level, so that's what it went. And I thank all the participants for patient listening, and I thank HOD sir, organizer Sunita madam for reaching out, and thank you once again for making me a part of this particular event.
Thank you so much, sir. Participants, again tomorrow morning on the same time by 10 o'clock, we'll be meeting with a new resource person. Hope you enjoy the day, and tomorrow we'll continue our knowledge gain. Thank you so much.
Sir, I request all the participants that only feedback form is shared in YouTube link and a Google Meet link only. Please don't ask us to post in WhatsApp also. Thank you all the participants. Please give your valuable feedback by filling the feedback form.